In this tutorial video we will be learning about Variational Quantum Eigensolver (VQE) with homemade Ansatz in Blueqat. We will be doing this in Google Colab. Like we did in previous video, we will start with installation of Blueqat. We can do it by using this code !pip install Blueqat. Type the code that was shown earlier in Google Colab. Then click on play button and Blueqat will be installed. Variational Quantum Eigensolver (VQE) using arbitrary Ansatz. When performing chemical calculations in VQE, the unitary matrix is operated on the initial wavefunction states, such as Hartree-Fock wave functions. And the unitary operation is determined by the Ansatz to be used. This time, we will calculate the electronic state of hydrogen molecule by VQE using Ansatz that we made by ourselves. We will use hardware-efficient Ansatz (HEA). First, we need to install the necessary libraries. The Hamiltonian is obtained with OpenFermion. Type the code shown and click on the play button. The libraries will be installed. Import the necessary libraries. The optimization of VQE uses SciPy minimize. Copy the code and click on play button. Definition of Ansatz. We choose hardware-efficient Ansatz (HEA). In HEA, firstly RY and RZ gates operate to each initialized qubit, and then CZ gates connect the adjacent qubits to each other. This block consisting of RY, RZ, and CZ gates is repeated several times. It is noticed that the types of gates and the connections are slightly different depending on studies. Physically, this Ansatz can be interpreted as a combination of the change of state for each qubit using the rotation on the block sphere by the RY and RZ gates and the extension of the search space of the wave function using the CZ gate. The arguments are the number of qubits n_qubits and the gate depth n_depth. The wave function is initialized in this function. Type the code shown and click on the play button. This segment of code is for wave function initialization. This one for circuit creation. And running the circuit. Expectations and cost functions. Get the expected value from the obtained wave function. Type the code shown and click on the play button. Obtaining the information of molecule. Specify the bond length of the hydrogen molecule and use OpenFermion to obtain information about the molecule. The basis set is STO3G. Type the code shown and click on the play button. You can get all the codes from the link in the description. Calculation, execution and plotting. Run a VQE on each bond length. This takes a few minutes. We then compare the results of the VQE and full FCI calculations with respect to energy and bond length. This segment is for recording bond length, HEA and FCI results. Next, for execute the calculation for each bond length. The next segment is for the determination of the number of bits, depth and initial parameter values. This one for defining Hamiltonian definition. Next, for optimization run. This one is for recording bond length, HEA and FCI results. The last segment is for plotting. Copy the code and click on the play button. Wait for a while and it will give you plotted graph. While depending on the initial parameters, VQE energy tends to deviate from the FCI energy in the large bond length region. The reason is that the prepared initial wave functions become different from the true solution with increasing the bond length. The accuracy might be improved by changing the initial parameters, ansatz, etc. That's all for today. Thank you.